Okay, so we know how to find now the vertical asymptotes, the holes, and therefore the domain of a rational function. And just as a review, we do that by factoring the top and the bottom. Next up, we want to be able to find the horizontal asymptotes. Which I will call HA for obvious reasons. Horizontal asymptotes looks like this. What I'm going to do is I'm going to use the exact same graph that we were using yesterday, this 2x squared plus 16x plus 30 divided by x squared minus 9. So f of x is equal to 2x squared plus 16x plus 30 divided by x squared minus 9. All right. Now, because I know in advance what's going to happen here, I'm also going to plot f of x is equal to 2. And you'll see why. So here's my 2x squared plus 16x plus 30 divided by x squared minus 9. Here's some other functions I'm not using right now. And also y is equal to 2. Now I'm going to expand my window a little bit. I need to expand my horizons. Negative 20 to 20. I don't really need the y values, just the x values. And when I graph this, there's my rational function, and there's my line y is equal to 2. And what you can see is that on the left-hand side, my graph seems to get closer and closer and closer to that y value of 2. On the right-hand side, it does the same thing, except instead of coming up from underneath, it's coming down from below, or it's coming down from above. All right, well, let's get into a little bit semi-formal definition of a horizontal asymptote. A horizontal asymptote is a horizontal line that the function approaches as x goes to infinity or x goes to negative infinity. Now, generally with our rational functions, it's going to approach the same number either way. Okay? That function that we just looked at, it approached 2 on the left, it approached 2 on the right. That doesn't always happen. So that's why I'm separating this. For most of our purposes for right now, then we will have the same horizontal asymptote. But I don't want you to get trapped into the line of thought that you're always going to have the same horizontal asymptote on the left-hand side as the right-hand side. What this can look like is we will wind up having a horizontal line here, and I will say it's at y is equal to b, okay? And right now I'm only going to look at right-hand side just because left-hand side, I think you'll get it, we'd just be going to negative infinity rather than positive infinity. As x approaches positive infinity, our function approaches that value b, whatever that is. You can also have a horizontal asymptote coming up from underneath. As x approaches infinity, f of x approaches b. And just so you see this, this is also possible. Since horizontal asymptotes mainly concern as x becomes really big, it's possible for our function to actually equal that value at a small value of x, and then as x gets really big, it approaches it. So, just because not all of our rational functions look that way, don't rule out the possibility that it can cross the asymptote. Okay, the asymptote is namely only for really large values of x. And thinking about that, wait a second, x going to infinity, x going to negative infinity. We've seen this. We've already done this with end behavior. It's the same thing. Let's say we have f of x. As a reminder, f of x is equal to 3x to the 5th plus 14x to the 4th minus 13x cubed. When we were looking at really large values of x and zooming way out, basically that function looked exactly the same as its leading term, 3x to the 5th. Those two functions, as you zoomed out, became indistinguishable because, as a reminder, when, for example, if x is equal to 100, x to the 5th, right here, is 100 times bigger than x to the 4th. It's 10,000 times bigger than x cubed. So when x gets really big, the other terms just don't matter. Well, we can use this when we're finding horizontal asymptotes. Let's look at the function we just graphed. F of x is equal to 2x squared plus 16x plus 30 divided by x squared minus 9. Okay, that's the one we were just looking at with the horizontal asymptote at y is equal to 2. Notice how, just like with vertical asymptotes, we're saying where it is. We're not saying horizontal asymptote is equal to 2. But also, since it's a horizontal line, then we have y is equal to 2, not x is equal to 2. X is equal to 2 would be a vertical line. So we have this information. We were able to find this from the graph. Well, let's see why this happens. As x approaches infinity, and in this case, it doesn't matter, positive or negative infinity. We could go either way. F of x really just starts to approach the leading terms on the top divided by the leading term on the bottom. The leading term on the top is 2x squared. The leading term on the bottom is x squared. You cancel out those x squared, and you're left with 2. So when x approaches infinity, and again, in this case, it's not always, but in this case, positive or negative infinity, then our function is simply going to approach 2. And we found that by the exact same way that we were able to look at end behavior in terms of a polynomial function. So here's the rules for finding a horizontal asymptote. Let's say we have, first I'm going to define our function. R of x, because it's a rational function, is equal to our numerator divided by our denominator. Okay, here's the first thing. You have to do this test before you do anything else. Otherwise, you might be led astray. If the degree of g of x is greater than or equal to the degree of f of x, okay? So if you have bigger powers of x on the bottom than on the top, then we have horizontal asymptotes. Or we have a horizontal asymptote, I should say. If it's less than, we got something completely different. So make sure that you do that test beforehand. Next up, we treat it like it's end behavior. We ditch everything but the leading terms. Three, we simplify. And four, if there is still an x there, if we still have an x floating around, see what happens as x approaches infinity or negative infinity to determine the horizontal asymptote. Okay? So let's try out a couple of examples and call it a night. Go ahead and give myself plenty of room and then scroll back up. There we there's our first one. And what I'm going to do here is I'm going to do really similar rational functions. I'm just going to tweak them a little bit to explore the different possibilities. 12x cubed plus 24 over 4x cubed minus 1. All right, the first thing we do is we compare the power of the leading term on the top and the power of the leading term on the bottom. We know that, let's put the bottom first. So 3 is equal to 3. Okay, so because that satisfies the term, the power on the order on the bottom is greater than or equal to, then we have a horizontal asymptote. So we have a horizontal asymptote. Check. All right, so now we know we're not barking up the wrong tree. As x approaches infinity, f of x is going to approach just its leading terms. 12x cubed, that 24 is just not going to matter if you're talking about x is equal to even 10, because then you'd have 12,000 over 4x cubed. When you simplify that, 12x cubed over 4x cubed is going to be 3. So what that tells us is we have a horizontal asymptote at y is equal to 3. Let's try it out. Got a whole bunch of noise on here I need to clear out. All right. First thing I want to graph, 12x cubed, 12x cubed plus 24 divided by 4x cubed minus 1. Notice my parentheses, you got to be catchy with those. We graph it. There we are. We have our horizontal asymptote right here at y is equal to 3, just like we thought. Okay, next up, I'm going to call this one g of x. 12x cubed plus 24, okay, so same numerator. All I'm going to do is I'm going to add another power on the denominator, 4x to the 4th minus 1. All right, so check. First thing we do is we make sure the power on the bottom is greater than or equal to the power on the top. 4, that is definitely greater than 3. So we have a horizontal asymptote. All right. X goes to infinity. Our function is going to approach 12x cubed divided by 4x to the 4th. That is equal to 3 over x. Wait a second, 3 over x, I've still got an x there. What do I do? Well, that's where we need that last little step there, where if there's still an x floating around in there, think of what's going to happen as x becomes huge, okay? As x becomes a really big number, 3, which is not a really big number, divided by a huge number is going to become a progressively smaller and smaller and smaller and smaller fraction. It's going to approach 0. In fact, just to avoid confusion, I'm going to write 3 over x is going to approach 0. Okay, so what that tells us is that we have a horizontal asymptote at y is equal to 0. Let's test it out. I'm going to go for the same function that I just did, 12x cubed plus 24. All I'm going to do is I'm going to trade out this 4x cubed for a 4x to the 4th. So I'm just going to make that 3 of 4. And I'm going to graph it. And lo and behold, there is my horizontal asymptote right there on the x-axis. You can see the graph rapidly approaches the x-axis there. All right, finally, let's try h of x is equal to 12x to the fourth plus 24 over 4x cubed minus 1, okay? So this time I put the fourth power on the top rather than the bottom. Other than that, it's the same as the other two guys we just did. Well, let's test it out. We need to make sure that the power on the bottom, or the order on the bottom, is greater than or equal to the order on the top. 3 is less than 4. Uh-oh. That means no horizontal asymptote. All right, well, now what? And basically where I'm going to leave you there is I'm going to say that's to be continued. We're going to get into that tomorrow. So for right now, just think about when the powers on the bottom are greater than or equal to the powers on the top. Here is your practice. Your practice is going to be on page 404. What I want you to do is find any horizontal asymptotes, if there are any. It's possible they're not. But find any horizontal asymptotes for numbers 1, 5, 7, and 9. Okay? Now that you see that you're basically ditching everything but your leading terms, I think you'll be able to go through those 4 relatively quickly. And with practice, you should be able to do these without really needing any calculations at all. Have a good evening, and I will see you in class.